Hi, this is Dr. Georgie. Today we're going to talk about scope basics in lecture 2 for Biosci 101. Before we do that, I just wanted to share with you some basic annotation and symbols that are used a lot in science. I might use them during the course of the semester, and you definitely should use them when taking notes. These are concepts that kind of come up frequently when talking about science, and so there's a certain way that scientists basically shorten them. For instance, down here you see these 3 dots. That means therefore. A lot of science is about cause and effect, or at least we're trying to figure out the causes behind what we see. So therefore is a word that comes up a lot. Also, be careful about using IE and EG correctly. IE means it is identical. For instance, Dr. Georgie, IE, your instructor for Biosci 101. EG is an example. For instance, community college instructors, e.g. Dr. Georgie, I'm one of many. I'm an example, but not the only community college instructor. I'm not the identity of a community college instructor. I don't define it. In science, we often use arrows to say, again, sort of a causative relationship, to say this, then this. Sometimes that means a cause, sometimes it just means one thing happens after another. And similarly, we use a line with a dash, think Diana Ross and stop in the name of love, that kind of gesture. That means the first thing in front of this symbol stops or inhibits the next thing. Again, a lot of times in science, it's about what causes something, what leads to, etc. And we also, just jumping down here to the middle of the slide, talk a lot about increasing or decreasing. So we just use arrows in our notes. Sometimes things go both ways. So double-sided arrow. We talk a lot about things being the same as or different than. So equal sign or equal with a slash for different. And last but not least, we're often recording or even trying to cause changes. For instance, from disease to health is a good change. And so change is just this little triangle. Again, a quick way of recording scientific notes. So let's go ahead and do a little activity before we dive into the lecture material. This is kind of a mini quiz just for, self-graded, if you will. Just take it at home and see how well you're doing at guessing the imaging technique or imaging modality. Same thing, right? But the point is, have you been looking at enough images to start to just recognize, oh, that was done with this, which technique, basically. So I'm going to give you a second to think or answer out loud if you feel comfortable doing so. Wherever you are, just call out, what imaging technique is this? How is this done? Yes, that's correct if you said fluorescence. So you can tell it's fluorescent due to a number of things. The characteristically bright colors, the green, red, and yellow, blue, are very typical of fluorescence, and also the super black background. That's a clear giveaway that you're looking at a fluorescence image. You've also seen this one before. Call it out. You've seen this one too. What imaging technique? What imaging technique was used to capture this lovely, cute image? I say ignore the color because the color doesn't give you info here about the technique, although it's nicely painted. The technique is, yes, SEM. How about this one? The technique is fluorescence. Again, the same usual colors. There's a lot of cells, so there's not a lot of black because there's not a lot of background. But again, DNA and blue, etc. What about this one? This one is phase microscopy. You can see the characteristic phase halos. It's a worm, and there are some phase halos visible. What about this one? What is this? What technique is this? It's obviously the muscle of a rattlesnake. This is TEM. It helps to know that these structures you're looking at are very small. These are all cells. But also there's the sort of characteristic grayscale TM with fine structures look to it. How about this one? While you're looking at it, I'm going to fix it because I can tell it was stretched incorrectly just because I know this image and I know what cells normally look like. So let's see if we can fix it a little bit. No, it's not letting me. Anyway, yes, this is fluorescence again. Very similar. This time the DNA is red. And how about this? Some beautiful bright field. This is H&E stain. This is made by a histologist. Beautiful slide. I think you've seen this one before. Do you remember what technique it is? Yes, it's TEM. Again, you're looking at a tiny part inside of a cell. So, you know, size is a giveaway, plus the characteristic grays there in TEM. Okay, on to this one. African water mongoose skin fibroblast cells. In case you're wondering, why do we care about the skin cells of a water mongoose? Probably it's because they grow well in a lab. That's a lot of the reason we study things. Also, all cells share similarities. Okay, time's up. Fluorescence. Yes, it is. How about this one? Hint, these are grown in cell culture, and yes, you've seen this before. Again, this is phase with the characteristic phase rings. How about this one? This one's new. Yes, this is TEM. And another really pretty one with a giant cell, probably this giant because it was grown in culture and cells just start getting a little bit crazy. I just realized I'm not in play mode. Let's see if it'll let me. There, so you don't see the images, stay on the side now. Again, the nuclei are blue. Yes, this is fluorescence. How about this? Oh, it's the same worm as before. Hint, it's not stained. Hint, it's not phase. Yes, it is DIC, the other contrast generating technique. Here's a lovely optic nerve, and yes, it's bright field. It's that characteristic H&E stain that histotechs are so well known for. And last but not least, one with the name on the slide. So it's a giveaway. This is what often is done with fluorescence is, so it's fluorescence and DIC both. Separate images were taken and they were overlaid so that the DIC shows you all the cells that are present, including a very rounded up one that may or may not be dying, depends. And you can see that there's a bunch of cells, but there's only 2 of them that are fluorescing. So this is a great reason why you often need to look at the same specimen with different kinds of imaging modalities. All right, let's go into scope basics now. Traveling light, because what we do is light microscopy, optical microscopy. Okay, so the optical microscopy is defined in large part by the journey of the light as it goes through the microscope. And so there are 2 fundamental ways that the light can travel. One is the light is going to go through the specimen. So you shine light and you watch the light path and you kind of guide it along so that it actually is transmitted through the specimen. The specimen alters the light as the light goes through it. And you collect the info, the altered light on the other side. That's what most optical microscopy does, is use transmitted light. And so again, the specimen itself has to be very thin. Otherwise, you'll just absorb all the light and nothing will come out the other side. However, instead of transmitting the light through, you can also choose to just reflect the light. In other words, have the light source on the same side as your sensor, as whatever you're using to collect your image, which is a camera or a sensor. Sensor is just a larger word for, just to say any kind of camera. So the light bounces off the specimen and is collected from the same side as the source of illumination, the source of light. That includes a dissecting microscope and, of course, our favorite technique, fluorescence. So a dissecting microscope is basically just bright field with a large field of view, and in a large, something known as working distance. Basically, you can put big things under there and use them to, yes, dissect them or just enjoy them. So here's a look at these two types of microscopes and microscopy. There's transmitted light and there's reflected light. The square is the specimen, basically. So in transmitted light, it goes through your specimen, and your specimen has to be able to let it go through. So it can't be opaque entirely. It can't be too fat. It can't absorb all the light. Or sometimes you just bounce it off the specimen. You might be surprised to realize that the way you see everything in your own world around you with your own eyes is reflected light. So there's light that from whatever light source is coming at you, and or let's say at another person who's in the room with you, and what you see is the light that is reflected off of them. Once again, two ways of approaching microscopy: transmitted light and reflected light. Transmitted light techniques include bright field phase and DIC. Reflective light is also known, techniques are actually often known as incident light or as epi-illumination. So once again, a lot of names for the same thing. And the big one that we're going to talk about is fluorescence. And when we're talking about a dissecting scope, often it is called reflected light. It's the same concept. It's just different fields use different terminology most commonly. All right, so let's look at transmitted light. So again, we're talking about the light has to go through the specimen itself, which has to be fairly thin, hence microtomy, hence histotex, or, choose a thin specimen. You either choose a thin specimen or have a histotech cut it for you, basically, if you're doing transmitted light. And the light source is on one side of the specimen, and the objective, which collects the light in the image, and your camera are on the other side of the specimen. Again, techniques that are transmitted light techniques include regular old bright field, phase, and DIC. Here's some images that you've seen before, just a reminder of these different techniques. A cheek cell is very thin. You can definitely pass some light through it. It's only about 10 microns. Actually, cheek cells are so flat and thin, they're about 3 microns or something like that. So super thin, or there's some tissue cut by a histotech, also super thin, just fine for transmitted light. So let's take a moment to think about light itself. We'll come back to this a little bit later in the class, but this is just sort of the first approach to what is light and what are the properties of light that are very important to us as microscopists. So light is described sometimes as a wave. When we talk more about light in a few weeks, we'll talk about how there's different ways of describing it. You may have already heard about this, but you can describe it as packets of energy that are known as photons, or you can describe it as a wave. Right now, we're going to talk about its wave nature. So it's energy that fluctuates. And the thing is, it fluctuates very regularly. And if you're measuring that energy, you can see that the energy fluctuates with a regularity um, that is measured in nanometers in space. And so there's this wave where the energy goes up and down, there's peaks and valleys. And if you measure the distance from one peak to the other peak, it has a certain length. That length is known as the wavelength, the length of the wave, and we process it in our eyes as color. So we register it as color. Blue light has a different wavelength than red light, for instance, and the length is actually nanometers. These waves also have a height to them. How high are the waves? Are they shallow waves? Or are they not so shallow? So there's how frequently they come and therefore how far apart they are. And then there's the height of them, which we call the amplitude. And it's technically half from the peak to the valley. But basically, the important part here is that we see it as intensity or brightness. So there can be red light and it can be really bright, or it can be really dim. There can be blue light, really dim, really bright. Just depends. Visible light is the light we're talking about by default. So when we say light, we just mean visible light, which is defined as light from 400 nanometers to 700 nanometers. It's visible because it's a light that we can process. Again, there are other forms of light that we cannot see and other forms of the same energy that we don't see with our eyes. So this is wavelengths of 400 nanometers to 700 nanometers. You'll see, I hope, at the AIM conference and in general with microscopists, people tend to talk about the light not necessarily as blue or green, but they use the actual numbers for the light because that's just much more informative. In terms of the colors, it's a rainbow starting with purple, if you will, as you see on this slide, to, blue, cyan, green, yellow, orange, and then red is 700 nanometers. Okay, so then this wave goes through the specimens. And as it goes through the specimens, there's all sorts of interesting, important changes that happen that we will, again, talk about more in depth later. But just to get your brain started to think about this, one of the things that can change is, of course, the amplitude, right? And so it can get less bright. Another thing that we are not aware of because we can't see it with our eyes, but actually happens is that the phase of the light changes. In other words, it gets the oscillations kind of hiccup. And if two light beams started out oscillating together, one of them is a little bit slow, is a little bit behind the other. It's kind of like, when you're taking the buses and, one gets delayed and then suddenly everything's kind of off. It's a little bit like that. It's a phase change. So our eyes don't see it, but scopes can actually report that out to you. And that's how phase microscopy works, and actually DIC also works. So here's just an example. There's an amplitude object. You can see it as a change in color, or as actually described here, really, it's a change in intensity. But the one I want you to really observe is the little drawing on the bottom, where you can see that that light wave is still oscillating with the same frequency. It's still the same color, and it's actually still the same intensity because the wave is just as high. The only thing is that it is slightly out of step with where it was before. So this is like the bus is now 5 minutes late to every stop kind of thing. And it's something that our eyes can't detect. If we see two light waves and one, they're both the same color, they're both the same brightness, but they're slightly out of phase, our eyes do not recognize that, but it's a reality. And phase microscopy and DIC microscopy can show it to you, basically. So specimens can be referred to as amplitude objects and phase objects. And phase objects are basically most things. It's basically, do they shift the phase of the light when when the light goes through them? Yes. A lot of specimens are phase objects. And how do you know? You just put them on the phase scope. Oh, look, I can see it. It's a phase object. It shifted the phase. Is it an amplitude object? In other words, will the light, when it goes through my specimen, will it change in color or intensity? If so, hey, I've got an amplitude object as my specimen. These terms are featured prominently in your in the Murphy-Davidson book, in your reference book. But to be honest, I'm thinking of taking them out of this lecture because they aren't used by real life microscopists much. It's a useful thought though, so just, you have to think about what's going to happen when the light goes through your specimen. Is the specimen going to alter the light? And the answer is yes, it'll always alter it some way. But will it alter the phase and or the amplitude of the light and also the frequency? Okay, so here's some useful info if you want to go play with this website. It has lots and lots of great info too. So light paths. Let's talk about how the light travels throughout the whole microscope. We're going to pause here for a moment, and there's a dramatic background here on your slide because this is a really important concept. So important. There's a lot of microscopes out there. Most of them don't have any sort of information attached to them on how to use them, nor can you look it up. Not even on the web. What I want you to be able to do coming out of this program is to approach an unknown microscope that you've never seen before, that no one knows how to use. This is a very real life scenario. So I want you to approach this unknown microscope that no one knows how to use and be able to figure out how to use it and use it well and use it correctly and get beautiful images from it. So the first thing to do when you meet a new microscope that you've never seen before is actually to stand there and stare at it. Yes, I mean stare at it. Don't go put your hands on it. Just look at it. Look at it more. I'm going to speed this up because, it's just a lecture, but take your time and look at it. And then without touching anything yet, you're still looking. Look to the side, look to the back, look all around the scope. What you're trying to do is to figure out where the light starts and where it goes. So you are trying to follow the light path. You're finding the light path, and there might be multiple light paths because there might be multiple light sources. And if you follow the light path for each of these light sources, you'll know what the scope can do. You'll know what kind of imaging modalities are possible on the scope. So again, when you see a new microscope you've never seen, stop, breathe, get excited, and then just look at it. Just actually look at it, study it. Find the illumination source, the bulb, the light bulb, basically. Or it might be a laser. It might be an arc lamp. find the light. Find the beginning of the light and follow the light path through the microscope. And then you'll know what the microscope does and how to use it. So let's look at some light paths on some microscopes. There's, I'm laughing because usually at this point, I just turn to some microscopes in my lab where I'm lecturing. But here, let's cut ahead to a picture so that we can have some microscopes. These might look complicated. They're not that complicated. There's these, back here on the back of them, you see these big old squares. Let's look at the one on the left. There's some big old squares here. Those are the light sources. They're encased in just a little cage because they get super hot and they have some little grill on top to let the air escape. So we can look and know that those are the light sources. And these are two types of scopes. One is upright and one is inverted. This is a fundamental thing about scopes. One of the first things that you're going to notice when you look at a scope, is it upright or is it inverted? And actually, I'm realizing I'll do some demos for you next week. Actually, I'll be at lab and I'll show you the light paths on some scopes since it's a little hard to follow here. But if you follow the light path, it will go through, like, let's say the one on the left, the bottom bulb, so that big black thing behind the scope, actually goes through the base of the scope, and then it goes up through the condenser, which is under the stage. And then you see the stage sitting there. It's where you're going to put your specimen. This one has a round stage, which tells me it's a polarized light scope. And then the light goes through the objectives and it goes on out to the oculars or to this weird looking camera that they've got hooked up. I find these scopes entertaining. We actually, the one on the right, we actually have some in our lab that are just in parts. Okay, so here's the thing. If you look at the one on the left, your objectives are on top of the stage and you can reach them and you can see them. They're right there, kind of where your nose is if you're putting something on the stage. On the one on the right, your objectives are going to look like they're hidden from you because they're in the bottom of the scope. And your lamp is actually on the top of the scope. So this is inverted because upright was sort of the first design, and then people invented the inverted scope, and it's actually the same light path. It's just flipped gravity-wise in terms of the light is at the top, and then it goes through a condenser, and then it goes through your specimen, and then it goes through the objectives, and then on out to the oculars or to, in this case, an old school camera. It's the same exact thing. It's just flipped over. And the reason for that is that in the inverted scope, it's easier to access the specimen. The regular type, the upright scope, the objective is right there and you kind of can't manipulate your specimen. With an inverted scope, do you see all that space right there on the stage? You could put a big fat dish of cells, for instance, which we do, and just focus in and up through the container of cells to find the one you want. This is basically a scope that is used for live cell imaging. So let's come back to this. So one of the first things that you're going to want to do is figure out, of course, what are your lamps, what are your imaging modalities? And then another really basic thing to know about your scope, is it upright or is it inverted? And the light path is actually fundamentally the same because here's your light path. It starts at the light source for the upright one, and it goes through a condenser, and then it goes through your specimen. This is transmitted light we're talking about. And then it gets collected by the objective, which goes out to the ocular and or the camera if it's a digital scope. If you look at the words for the inverted, same exact thing. Light to condenser through the specimen, collected by the objective, out to the ocular and camera. The only difference is what side of the specimen the stage is on. That has to do with gravity. It's just like, is the stage holding your specimen from here or from, above or below? Just depends on whether the light is near your head or near your feet, so to speak. And what, are you going up or are you going down? So upright, the light is at the bottom and it goes up through the specimen and out through the objective. Inverted scope, the light is at the top and it goes down through the specimen into the objective. It's the same fundamental journey. It's just, one is doing a handstand basically, right? So upright scope and inverted scope, that's a first first thing to look for in terms of looking at your scope. Now, if we're talking about the light path of transmitted light, which is usually bright field of some sort, including phaser DIC, versus the light path of epifluorescence, also a reflected light, incident light, anything like that, the light path is different. So let's look at it. Transmitted light, the light starts out at the bulb, goes through the condenser, goes through your specimen, to the objective, and then out to the ocular and our cameras. For epifluorescence, the light starts out, it doesn't go through a condenser. It goes through the objective, hits your specimen, goes back up through the objective, and then out to the ocular. So, wow, where's the condenser? There isn't one. The objective acts as a condenser. And in fact, half of the scope is not used. Only part of let's just look, actually. Here's a little drawing of a scope. So here's, first thing to notice, it's an upright scope with two light sources. You see the bright field source is on the bottom, and it goes through the condenser, gets transmitted through your specimen, and then goes on out. The epi-illumination source or fluorescent source starts at the top in this case, and it goes through the objectives. I sometimes say oculars for objectives, but hopefully you catch me if I do that. So it goes through the objectives, and then it hits your specimen, more light is created, and that light follows the sort of second part of the journey, same part that the bright field light took, part B, basically. So that orange line A1 to B, that is fluorescence. You can see that it's only using the top half of the scope, right, up to this stage. Anything below the scope, the condenser, the lights down there, doesn't matter. It's just that sort of half of the scope. The bright field light path uses the entire scope. It's A2 to B. This is what it is. So this is fluorescence versus transmitted light on an upright scope. Here we go with transmitted light versus fluorescence, but this time on an inverted scope. So this time the scope is, if you will, upside down, and the bright field source is on the top. And we have A1 to B as the bright field light. And basically it's going through the condenser, through your specimen, and then through the objectives, which are down there in the base of the scope, and then on out to the camera or the oculars. In the case of fluorescence, fluorescence is all going to stay on the same side of the stage and only use half of the scope. So in this case, the case of an inverted scope, the fluorescence illumination source is on the bottom, and we have the pathway of A2 to B. So the fluorescence light goes through the objective, hits your specimen, and we collect again through the same objective, and then send it out. By the way, there's mirrors, etc., inside the scope. So we send it out using mirrors and things like that, out to the oculars or to a camera. So in this inverted scope, you're only using the bottom half for fluorescence, and the objectives are down in the base. And again, the condenser is not used at all in fluorescence. So let's talk a little bit about the various parts of a microscope. Here we go. This is actually one of the scopes that we have, and I'm going to give you a second to think if it's upright or inverted. Actually, I'll go through these parts, and then after that, I will tell you the answer, so to speak. So you need an on-off button. So you have one for the lamp. At the front, there's something called a rheostat, which is basically a way of controlling the intensity of your light source. We have the coarse focus and the fine focus, which we're going to talk a lot more about later on when we get to how to use this scope. So that just moves your specimen into the proper place in the direction of up or down, let's just say for now. We have the stage controls that move your specimen around from left to right. We have the, it's a little hard to see, but the nose piece is it's a rotating piece of metal usually that the objectives are in, and then we have the objectives. In this scope, I pointed out we have a fluorescence filter slider. We will come back to that way later when we're doing fluorescence. There's the stage. The stage is just the rest, the part that you put your specimen on. Up there above it, there's a condenser. There's a phase slider, which is the part that's used in phase microscopy. And then that tiny little thing that isn't even labeled, that little gray square going up past the phase slider, that's actually the world's smallest bulb housing that I've ever seen on a scope. So there's a bulb in that. So that's the light source for bright field. And of course the oculars are the part where you put your eyes up to it to look. So hopefully you've by now figured out that this is an inverted scope because the objectives are down under the stage and the condenser is up above the stage. I wanted to show you early into this class a little bit about an objective. So you don't have to know all of the parts on here. In fact, I'll never ask you all of the parts. But what I want you to notice to see is that inside an objective, there are a lot of lenses, not always this many, but sometimes. So the little lens that you're going to clean is what is known as the front lens. But if you cut into an objective, which you wouldn't do, but let's just do it as a thought experiment, you would find that there's a whole series of lenses that are placed there. This is why objectives are so amazing and expensive and hard to make, and only good ones are only made in certain places in Germany and Japan, to be honest, although I've seen some good ones coming out of China now. So it's a very specialized kind of thing to create a proper microscope objective for these days. And the good news is there's a ton of info on the objective itself that tells you all sorts of things about it. And by the end of this class, you'll know what info is told to you right there written on the objective itself. So just notice objectives. They're kind of maybe the most important part of the scope. If you made me pick one part, okay. There's a lot of magic in having a good objective. It makes all the difference. And last but not least, I need to talk to you before we go any further into this class about cover slips. Because of course, you know that our specimens are going to be put on a big old glass slide, which is nicely transparent. And then you're going to put a cover slip on top of it, which is another really thin piece of glass. If you were taught in microbiology not to use them, forget what the microbiologist taught you. They're wrong. Everyone else in the world uses cover slips, and you should, to protect the scope. So cover slips. Here's the weird thing. Well, I think it's weird. The weird thing is that they come in all sorts of thicknesses, also all sorts of shapes. Shapes is fine. That's just do whatever works for you for shape. But here's the thing. There's only one thickness that works on pretty much almost all those scopes. Why they make all these other thicknesses is beyond me. So don't fall for it. All you ever want to use is 1.5 thickness. I mean 1.5, number 1.5, which varies in the actual thickness from 0.16 to 0.19 millimeters. It's hard to make cover slips, and it's fine as long as there's just one cover slip. Frequent mistake is two are stuck together and then you can't see anything. But as long as you're using one and it's not too fat, your microscope will work. If you're using the wrong thickness and it's too thick, you won't be able to focus. So just double check that you're using a 1.5. Even a number 2 thickness will not work on most scopes. You can use something thinner, sure, but even a number 1 is so fragile. You have to be super careful, and really there's not a lot of point in using it. So really all we ever live with most of the time are number 1.5 cover slips. The rest should just be abolished, and they can be used for specific reasons in rare instances, but unfortunately you find them flying, in labs all the time, messing people up, and people are using them going, I can't focus, why? And one of the first things that I look to is how fat is your cover slip anyway? Okay, so now and you know that we use and love number 1.5s pretty much exclusively. That's it for today.